Hey, welcome to our class today. It's going to be AH-360, the lecture portion. So just to start off, the first thing we should do is take a look at your assessments, what remained. So this week, so you're supposed to be delivering lab number 3. So make sure you submit lab 3. Make sure you submit it. That's due today. And next, so it says week 12, but it looks like, and so this is week 12. What does that mean? The AOC assignment is due the 30th of March. So let me know if you need more time for that, just in case. And then the term report after that. Now, 6th of April. So these are a couple of the main items coming up, especially these. Now, next week, we have our lab on 26th. So for that, I would suggest you either work on lab 4, part 1, if you haven't, or if you want to take a break because it's not due, or work on the AOC assignment. We'll work on the AOC assignment or term report, term project. Okay, so those are key. But we'll probably have our final or one of our last few lectures on. So we'll have our lecture on the 28th. Online, but also a work session. How does that sound? So next week, we use both sessions to finish these assignments, especially the AOC and the term report. And then on the 4th, sorry, and then on the 2nd, you will be going to the organic waste lab, organic waste plant. So that lab can be replaced by the class. Sorry, that lab will be replaced by Andrew's class on the 3rd. And then on the 4th, we'll have our lecture or our lecture/lab session in person. The only thing is then you'll have to bring your own computer. And that's also the day the city is coming, the city staff. Then we have our lab session on the 9th, where we're going to go to the wells. On the 9th, we go to the wells. Go to the wells. And then on the 11th, it's our last lecture. And we start our final assessment. And we also have a guest that day. So that's sort of the roadmap for the rest of the semester. Do you guys want to just use next week to work on your projects? Because we're ahead on the lectures, like I said. And one of our workshops had to be canceled. It was more, so that's why James did the soils yesterday. So we're a little bit ahead on the lectures because we combined two workshops yesterday. How do you guys feel about that? So next week we can work on lab, so we can work on lab number 4, part 2.
That works, Professor. That works.
And in the lecture session, you can work on completing. You can work on completing your assignment. And then the following week, your lab will be going to the organic waste plant. Okay, so that is that. Okay, so something I want to talk about now. So let's take a look at a scenario where you have a so we're basically moving on. We're gonna start talking about spills. But before we do that, I just want to rehash a few things. But as you guys remember, if you have groundwater data, so what does that mean by groundwater data? If you have groundwater elevations and you plot them on your map, you now have the ability to determine groundwater flow, especially if it's in a triangle, right? Let's say it's not a triangle here, but you've actually got the elevations. We'll put it in different colors. And how did you get that elevation? You measure the water level. So let's say this is a 131.10, 136.22, 135.11. It's not always this simple. And you've contoured it, whether you've done it with your hands or done the contours with a software. So let's say we're going to use 132. Okay. And then you want to label it. So it's in meters above sea level. And then you've got 133. One 134. We've got 135. So here at the groundwater, it's quite, actually, this should never be touching. You've got the groundwater, it's quite steep. When the contours are closer together, the gradient is higher. Because what's happening here, what you've just mapped here, is just imagine it's the cross section of your site. Let's say this is monitoring well 1, monitoring well 2, monitoring well 3, monitoring well 4. And let's say you've drawn a cross section A to A dash. That's A to A dash. It's monitoring well 2, and then monitoring well 3. Essentially, what you're basically showing here is, see, the dip is much steeper over here. And you guys did this in topography, so I don't want to spend too much time on it. But another thing I wanted to point out is you can now, with this information, determine what DH is. What is DH going to be equal to? The difference in the groundwater elevation. Let's say we're trying to determine the groundwater flow. Let's use this. So it'll be 135.11 minus 131.10. DL is the distance between 1 and 3. Let's say the distance is 67 meters. So that'll be 67. Go ahead and calculate that. 135.11 minus 131.1, 4.01 divided by 67.0598. This is equal to 0.0598 meters per meter. And what is that? That is also known as the hydraulic gradient. That's known as a hydraulic gradient. Now, if you know the K value, you multiply it you can multiply it. If you know what K is, let's say it's 10 to the power minus 4 meters per second. You just multiply that by dH by dL. And this gets to be 10 to the power minus 4 times 0.0598. So this is equal to 5.98 times 10 to the power minus 6 meters per second. Or you can actually determine, you multiply that by 60, that's equal to 3.59 times 10 to the power minus 6 meters per minute. You can multiply that by 60, it's equal to 215.46 times 10 to the power minus 6 meters per hour, which is also equal to 2.15 times 10 to the power minus 4 meters per hour. Now, how far will it go in a day? So now that's equal to 51.71 times 10 to the power minus 4 meters per day. That's pretty quick. Like, and where does that become important? Where does that become important? So let's consider a situation where you are performing a site assessment. So let's draw your site. That's your site. And you find in your study that there was a gas station here, and the ARIS report says there was a leak or spill and it was underground. Now, maybe you found this out through a record of site condition. And you know, based on the map, that the distance from your site is 44 meters. You also know, based on your study, that there's a water body nearby, a creek. And the dip of the topography is in this direction. So you surmise that this is where the groundwater's flowing. Now, based on that information and the calculation that you just did, that it goes 55 meters a day, there's a likelihood that your site could have been impacted. And this is the PCA. So this is the PCA. And this is the area of concern. So this is where you'd put your wells. Let's say you found contamination. Let's say you found contamination. So what are some of the options? And that's where we are getting into now. How do you respond to a spill? Spill response. So we'll go over some of the technologies and methods that you respond to spills. So first, let's consider a scenario. So we're going to go back and forth, but there's two or three types of spills that I'm going to talk about. One is the subsurface. So you're dealing with groundwater contamination. Two is a limited indoor spill. So it's basically superficial. And then there's the major or larger scaled exterior spill, like a railway track. So, and we're going to be jumping back and forth. But in this situation, what we have is we have our site. We have our site. And we know, and let's say we did the study, and we know that we've got contamination because a bunch of the wells came out impacted, and we've delineated that the contamination is limited to this portion. Now, let's say you clean up the site. How do you clean it? Well, there's different methods, but right now, let's say you've cleaned up the site. What's to stop the spill from continuing to come? Is there anything to stop it from continuing to come? Well, actually, no. But because you've done your groundwater studies and you know the direction, so let's say here's the plume. It's the ground surface. Here's your site. And groundwater is flowing in this direction, meaning the plume is flowing like this, and it's entering your site. So in the subsurface, your site boundary is here. So what can be done? What you can do is install what is known as a permeable barrier at the boundary. What you do in the permeable barrier is it's a mixture of sand and zero band iron, or ZBI. There's companies that can come in and create that trench for you. It's also known as a permeable reactive barrier. So what happens is when the groundwater flows through, it's getting treated. Let's see if I can find a good one. Let this property. Groundwater in the subsurface. You're installing the permeable reactive barrier. By digging the trench. So that's one method, a permeable reactive barrier. Another method is a Waterloo barrier, just putting a wall. I'll show you how that's done in a second. Waterloo barrier for the groundwater. So especially done when you've got a lot of contamination that you just want to keep out. Let's see. Waterloo barrier. So you know what? I'm just going to explain it here. I don't need that. In case of a Waterloo barrier, you do it slightly differently. So you got your contamination, it's coming to your site. You can't really stop it. And the client says, no, I'm not going to build a permeable reactive barrier. So they said no to a PRB, permeable reactive barrier. They've already said no. Got your contamination flowing onto your site. Site boundary. So they said no to the barrier. So what you can do is that, let's say you've got bedrock at about 30 feet. You've got bedrock. And it's consolidated, so you know that the groundwater is not flowing through it. where you got this plume. So you can actually go back and install at the property boundary a Waterloo barrier, a Waterloo barrier, which is a steel wall. To block this contamination from coming onto your site. So the hope is over time that it will attenuate, but maybe it won't. So I'm going to share with you something that you might find helpful. Some information on permeable reactive barriers or treatment walls. The concept has been around for a while. But essentially, you've got your contaminant source, the flow direction of groundwater, and the treatment wall, which now allows for treated groundwater to flow through. They don't have to be all the way up to the surface, but they have to be set up in such a way that they cover the groundwater column. Sometimes you might have to replace the material, dig up and replace it to refresh it, depending on how much contamination you're dealing with. But the first step is always to characterize the site, do some hydrogeologic modeling, do some aquifer testing. And then based on the contamination that you're dealing with, you want to set up the wall with the proper treatment mixture. Like I said, we usually use ZVI, and this is not commonly used for anything other than organics. But different companies have different methods to dig it. And the company that we've used in order to dig this is known as D-Wind. I mean, hold up, D-Wind. They're an excavation company that does trenching. I haven't been involved in such a project in a little bit of time. They will go ahead and in one pass create the trench, and then you can install your barrier. Because what used to happen in the past is we would have to go out to the site with equipment and install the barrier.
Mitsubishi Motors.
They do pretty good work. All right. But in order to understand What do you need to know? That's one way to deal with the water. Another is now you've got your site. So you've already dealt with the offsite, right? Got your trench, but you still have contamination at your property. So the trench is blocking the offsite. But what about the plume that's already on site? What do you do about it? What do you do about this plume that's right here? So there's a couple of methods. There's a couple of methods to deal with it. Number one, pump and treat, or exitu. That's one. The other is ISCO, or in situ chemical oxidation. So the first is as it implies, it's pump and treat. You could put a well into the ground or a series of wells, and you pump it out. What you're trying to do is pump out the contaminated material. And then you send it to your mobile treatment system. Remember, you designed it last semester. You're pumping it out. Before you set up the pumping system, what do you want to know about the site? Again, you have to do site characterization. And the second method is in situ chemical oxidation. You've got your site, got your groundwater plume. It's the groundwater, but it is infested with a plume. You can now perform what I said earlier is in situ chemical oxidation by injecting. So you can inject chemical like potassium or manganate or sodium peroxide. I don't remember the chemical formula, so I'll actually write it as sodium peroxide. You can also use sodium persulfate. What it does is it oxidizes the chemical. In this case, you're pumping out chemical into the ground. create a scenario where your oxidant is breaking down the material. Let's watch this animation of how in situ chemical oxidation works. One of the companies that does this is
I
known
love
as
Monday.com.
Genesis.
Monday.com. You don't know Monday.com? This is Monday.com. Hello. I'm Dr. Jeremy Jones, Managing Director of Genesis Stores. On behalf of the entire company, I'd like to talk to you about what you should know about the chemical oxidation right on planet. In situ chemical oxidation. A reagent to oxidize these contaminants.
Contaminants. There is also a larger big group of treatment technology called in situ chemical oxidation, ISCO in short. That utilize different type of highly oxidative reagent to oxidize these contaminants. So how does in situ chemical oxidation work? So basically, we have a big plume of contaminants in the subground in this slide shown in this orange color. And then when we are going to treat the organic contaminants, we would have a truck loading with reagent. Then we inject this type of reagent into the subsurface. And then these reagents react with the reactive phases of the soil minerals to generate highly oxidative oxidants. So the oxidants permeates into the subsurface and then oxidize the contaminants. Basically, the traditional used oxidants for this in situ remediation include hydrogen peroxide. So if we look at the chemical structure of hydrogen peroxide, it has a peroxy bond. And it is because of this peroxy bond that is responsible for the highly oxidative properties of this chemical. In addition to hydrogen peroxide, a very similar compound is called persulfate. Basically, persulfate shares very similar chemical structure with hydrogen peroxide. It still has the peroxy bond, but instead of a hydrogen bonded with an oxygen, it is a SO3 group bonded with an oxygen. So how does the sulfate radical formation proceed via the persulfate activation? In the subgrounds, we have many different types of soil particles enriched in iron elements. Basically, they are iron oxide or in +3 oxidation state. So when we start to inject persulfate into the underground, persulfate oxides react with iron 3 through an one electron transfer process as a redox chemical reaction. So persulfate is oxidized into persulfate radical, and in turn, iron 3 is reduced to iron 2 in the soil particles. But this is just half of the reaction. And persulfate then reacts with the reduced form of iron, which is iron 2, and oxidize iron 2 to iron 3. And the persulfate itself is activated into a sulfate anion, and more importantly, a sulfate radical. So sulfate radical is a very oxidative radical species that can be used to oxidize those contaminants in the superfund sites. And because this is the redox cycle between iron 3 and iron 2, it activates the persulfate into sulfate radicals. So it's it is a catalytical reaction process controlled by the iron minerals in the subsurface. Similarly, when we inject hydrogen peroxide, it is the same catalytical reaction that produces hydroxyl radicals from hydrogen peroxide. So hydrogen peroxide reacts with iron 2 to form hydroxyl radicals, and then hydroxyl radical react with contaminants and oxidize them into less toxic forms. However, there are, besides this main catalytical process to generate hydroxyl radicals, there are also other scavenging effects, scavenging reactions that reduce the efficiency of the generation of these highly oxidative radicals. Some of this process include, first, hydrogen peroxide can react with iron 2 through a 2-electron transfer process, and instead of producing hydroxyl radical, it produces just water molecule without
so he's talking
any
about the research.
oxidative species
I was
generated.
hoping to show
And
the actual
hydroxyl radical
animated.
can also
But that
react
gives you a
further
gist.
with
That gives you a gist of what's going on in the subsurface. Hold on. And then on the surface of the site, this is what the setup looks like.
Advanced security features.
So this is how it basically mixing in a big batch. This is always very, very challenging. You can easily burn yourself. I don't know why this person doesn't have a hazmat suit on. And then here you've got your injection points with the pressure valves and the pressure gauges, the flow meter, and the valves.
Hi, my name is Craig Sandifer. I'm Vice President for Technology at Regenesis. Today, we're going to talk about sulfox, catalyzed persulfate, with our inline pump here, an AH-25, and I'm going to be mixing it in a 250, 300 gallon tank with approximately 125 gallons of water. We need to have proper personal protection. For me today, that's going to be steel-toed boots, eye protection, and a dust mask. For you, on your sites, you should be consulting your health and safety officer. Now, my mixing configuration today is composed of an inline pump and a lightning mixer, vortex mixer. And your options are many. You can just use a vortex mixer, or you can just use an inline mixer. Your goal is to recirculate and move the material to solubilize this material. It takes about 15 minutes to do that, and whether you use a vortex mixer or an inline pump to do that, it's completely up to you and your configuration and your needs. Okay, a little more detail on the mixing side. I've preloaded 125 gallons of water into our 300 gallon tank. So here's our water level, and you can see everything is connected up to our pump from the tank. We have in fluid and effluent out of the pump. And we've also added a lightning mixer. This is just a traditional vortex mixer. So we'll use both the inline pumping machine as well as the vortex mixer to mix up our persulfox. Now, in most applications, the field personnel should allow themselves roughly 15 to 20 minutes to mix a batch of persulfates. So given this kind of setup,
So this is exactly how it looks. The ISCO mobile treatment plant treatment system on the surface. They used to have it automated in many sites, but here in Canada, it turns out to be a disaster if things go wrong. And that's why actually having actual human beings on site as opposed to robots or running the system remotely it's key so that nothing goes wrong and you're not really seeing chemicals being injected and going the wrong way or having humans exposed to the chemicals or the system breaking down on site. As you can see, there's a lot of things that can go wrong. And right now you're looking at picture perfect. This could be Florida or someplace warm. Are we going to get these conditions in Ontario all the time? Of course not.
count on about 15 to 20 minutes. In this next segment, I'm going to show you how I load persulfox to create a 15% solution, load that into water. And as with all the oxidants, you need to use proper PPE. So I'm going to put on a dust mask and I'll show you what I consider to be best practices for loading persulfox to create the 15% solution. Now, the bag I'm going to be using today is our preferred packaging. It's 55.1 pounds or 25 kilo bags of persulfox.
Recirculation, because otherwise there might be residue at the bottom. And once it clears up or looks the same color as the overall mixture, you don't need to keep it recirculating.
So I've been mixing our 15% persulfox solution for about 10 minutes or so. You know, we're almost where we need to be on the material. As you can see, it's very soluble.
But now once his solution is ready, he's going to basically pump it into the injection wells, into the injection points.
100% soluble. And after you're about 15 minutes of mixing, you should be ready to go.
So that, now let's take a look. So once you've injected it, you tend to then let it sit and you wait depending on, this was actually not, this is a catalyst. So what that should was hydrogen peroxide. So let me correct myself. But if you need to use a catalyst, sodium peroxide is used. But the actual oxidizer might be hydrogen peroxide or sodium persulfate. These were two of the common ones. Another one is potassium permanganate. So once you've injected the material into the ground, you let it mix and work on the different areas or locations of the contaminants. So you wait about 3 to 6 weeks, depending on how much you've injected, and then you sample the groundwater again. Now, if you're using injection wells, you're supposed to have separate monitoring wells. So maybe you've got a monitoring well in between, monitoring well over here, to see how the progress is. And this is where it becomes interesting, especially in the reporting phase. So let's say you start off at, let's say, monitoring well 6. And you've got the contaminant concentration. So let's say it's a concentration of, let's say it's, in this case, it's TCE. And this is, you're sampling every 4 months. So let's say this is October, January, or February, and then May, and so on. What you're hoping to see is the concentration of the contaminant, especially if you're aggressive, to dip. And if the standard, MECP standard is here, you want to see it dip to below that level over time. Now, a question for you guys. Let's say the cutoff date for the injections, I'll do that in green, the cutoff date for the injections and off injections, because remember, you wait 4 weeks, you come, you sample, then you come back and inject again. End of injection program. Let's say you've injected here at the start, you inject again, you inject again. Now that's the end of injections. Should you just leave the site and never test again? No. Once the injections end, you need 1 year of monitoring, sampling and monitoring. Okay. All right, so let's take a short break and then we'll actually get into some slides for ISCO remediation. All right, so let's take a short break. I'll see you guys in about 5 minutes. Okay, so the next main thing that we're going to talk about now is what do you need to know before you can practice this type of injection or practice this type of. But just to summarize, you guys remember in the pump and treat, the typical treatment train when you pump and treat is you might have a settlement tank. Remember a settlement tank, and then you'll have filters. And then you might have granular carbon vessels. Or and depending on the contaminant, you might even have activated aluminum. So this would be for pump and treat. But I wanted to mention to you guys something. 9 times out of 10, you need to supplement the pump and treat with some form of in situ chemical oxidation. Why? Because our experience shows that in most sites, so let's say you've got a contamination level that's over here, right? And you're trying to achieve a cleanup level that's over here, according to the Ministry of the Environment. So these are the concentrations. This is time. Pump and treat has really, really good initial results very quickly within weeks. Concentrations tend to go down. But for whatever reason, it seems to plateau and even come up a little bit over time after done that. After you've done the initial pumping. But this is where it's important to understand several things before you perform a cleanup at a site. So what do you need to know? What do you need to know? To create a spill or what do you need to know? Does anybody want to help me with this? So what do you want to know about the site? What's the first thing you want to know? It's a subsurface spill. What do you want to know? How about the contaminants, the concentrations of contaminants and compounds? So what are the parameters? What else do you want to know? What else do you guys want to know? So this is, you're going to tell me what you need to know. So I'm going to break you up into groups. And in your group, you're going to list at least 3 things that you want to know before you can treat the spill. To make a breakout room. So I'll give you guys 3 rooms. Okay, so it'll be 3 participants per room. All right, so the rooms are open. So Adarsh, Cody, Jason, you go to room 1. Room 2, it's Jinu, Crispin, and Cynthia. Room 3, it's Bijal, Emmanuel, and Sophie. So I'm opening up the rooms now. Adarsh, Crispin, Beetle, if you guys could join your rooms. Beetle, if you could join your room. Okay, so you have about 10 minutes to come up with at least 3 things that you need to know about the site before you can perform a remediation project. I will close the room in about a minute or so.
Cute cat, Professor.
Pardon me?
You have a cute cat.
Thank you. Well, I'm just waiting for a couple of people to return. Oh, she's fighting with me. Still in her kitten phase.
Oh no.
Okay, so room number 1. What is it that we need? What is it that we need? No, before we can respond to Bill. We started off with concentrations and the compounds of concern, the chemicals of concern. What else would we need? Who was in room number 1?
Myself, Cody, and Adarsh, Professor.
Okay, so what would we need? What do you need to know?
What do you, well, from what you talked about,
Yeah, you're cutting out.
would that, oh no. Could I ask Cody to speak on my behalf?
Well, it's okay. So
I've typed it in the chat.
yeah,
Sorry.
flow direction, 100%. Flow rate, yeah, flow rate, or
We also
velocity.
need, sorry.
Yeah, go ahead.
We also need to determine the amount of time that has actually elapsed since the spill happened so that we can
Yeah.
determine how far it's traveled so far.
Yeah, so that sometimes you have that information, sometimes you don't.
Oh,
So
I see.
time of event is definitely crucial. Yeah, if we have it. Okay, that's perfect. So that's actually exactly some of the information that I was hoping that you would come up with. Source, yeah, the source. What caused the spill? 100%. Okay, room number
Right.
2. Room number 2. Who was in room number 2?
We can say that the type of contaminants, whether
Okay.
it's a VOC or
Yeah, so that's that. Yeah, true. What else do you think
like
is missing
what
from?
And if we are sampling the soil, and how much depth we are gonna
How would
do?
you know
We are
this
going to do the
before?
remediation.
Like, how would you know this before?
So we need to know the permeability,
Yeah, so the permeability, right? The aquifer parameters.
the aquifer parameters.
Professor,
So,
can we also check the wind direction, like for airborne?
so for a groundwater spill, it has no relevance. But for a surficial spill, yes, you would. But if we're talking about a groundwater spill, the wind doesn't impact the process because the amounts of concentration in the air are usually not of a concern.
Okay.
But that would be the case for a surficial spill for sure. Okay. So Chinu, you were asking if we should know the depth of the sample?
No, I was saying about the permeability, like how
Yeah,
far
yeah.
is it?
Yeah, you
Yeah,
need to do the
that's what.
aquifer
Yeah,
parameters. So
yes.
And then the last one is we need to determine the area extent of the
yeah,
contamination.
delineation, if you can. Yeah. So I'm going to touch on these points, and then we'll continue the conversation. So let's say you have a bunch of wells that you drilled on site, and you tested the aquifer, tested the groundwater. So since we're dealing with right now just groundwater spill, we're going to focus on groundwater contamination. Okay. We will spend a little bit of time on doing an excavation in the waste portion of the other course, but here we're going to focus more on the groundwater contamination. So what Crispin just mentioned, which was excellent, was if you found contamination, how far do you think it went? How deep do you think it went? So that's what it's called. What you do, this is the horizontal delineation. And then you might also want to know how deep it's gone. That's the vertical delineation. So I'm going to explain why this is important. I'm going to explain why this is important. And in order to do that, you add more wells. Why this is important? So let's say you have the aerial extent of the plume on your site as 700 square meters. And you've determined the aquifer thickness where it is. It's from a depth of 2 meters to 4 meters, which is equal to 2 meters thickness. So that means the volume of the plume is 700 times 2 is equal to 1,400 cubic meters. Now, your concentration of contaminant, let's say just for one contaminant, we're not going to, it's vinyl chloride, VC, and it is 24 micrograms per liter. Right. So what is the contaminant load that you're dealing with? So the contaminant load can be calculated because that will help you design the treatment project, like how much chemical you need to inject, how long you need to inject, at what depths you need to inject, and what frequency, and also the concentrations of the chemical oxidant. So that's beyond the scope of this course to determine those things, but that's what you would need to know. So the contamination or the contaminant load helps you design the overall project. That's going to be equal to, so it's 1,400 cubic meters is the volume. But is that really the volume? Because if the porosity is 25%, then the actual volume is going to be 1400 times 0.25 times 0.25. And what is that equal to? 350 cubic meters. Convert that to liters. What is that equal to? 350 times 1,000 is equal to 350,000 liters. We have 24 grams per liter. So total micrograms, sorry, total micrograms is equal to 24 times 350,000. What is that equal to? 8.4 million micrograms. What is that in grams? 8.4 grams. That is the amount of actual chemical VC that you're dealing with. And you can design it accordingly. So that was one of the things you guys mentioned, which was excellent. Another thing which we've already determined, flow direction, right? We've already talked about how to determine that at your site. Flow rate. So this is where it becomes extremely dicey. So we're gonna do this a little bit carefully. But this is a part of your lab 4. So remember I talked about the slug tests? We're gonna get into that detail now. And so it's a long video, but it's important. We're probably gonna split it up. Slug tests to get the aquifer parameters, flow rates, etc.
Just opening up the monitoring well. Sometimes some debris, some soil gets in the hex inserts. It's nice to have a little pick or small screwdriver to clean out soil and debris. Open up the lid. Next thing we're going to do is a well verification. Going to use the solid water sounder to measure the depth to static groundwater level and also the total depth of the well. So I'm just going to unscrew it and take out the plug. And we'll make our measurements to a common data point. The data that I have that has been surveyed is to the south side of the 2-inch casing, which in this well is in this direction. So again, make sure your saltness is working. Put the sensitivity all the way up. This probe has already been decontaminated, so it's fine to put in this well. So we always want to be careful not to cross-contaminate our wells. So we'll just lower it carefully to get a depth of groundwater. Again, the measurement is to the top of the casing, not to the top of the well.
So the way the water level meter or the water level tape works is it has a wire, 2 wires running parallel that are not connected. But when it touches the water, the circuit is complete. So the electricity is allowed to flow between the wires through the water. And that causes the beeping sound. And that's how you know what depth the water is at, right? And then there's a measurement on the tape that the probe is attached to that you can now determine from the ground surface what the water level is. So in this case, he's doing everything perfectly except one thing. In general, they would probably ask you to wear safety glasses because you're not really sure what the level of contamination is in the well, so you don't want that to be entering your body through the eyes. Secondly, things happen on site, so you want to protect your eyes at all times.
Dip it a couple times. So in this well, it's 2.7 meters. The water level. I'm just going to turn off the meter right now. I'll just continue running in the probe just to get a TD measurement. Just going gently. There's no point in ramming down. The well isn't that deep. Damaging the equipment, damaging the probe.
One of the best skills you can have is being able to protect and maintain and treat your equipment in a way that it doesn't break. Once in a while, it does happen. It's happened to me a few times where things are broken. But if in general you were able to maintain your equipment very well in the field, your company will really like to keep you employed because they like to have people who take care of the items that the company owns or rents.
Okay, I've hit bottom. Just going to come off it, on and off it again a couple times. Just get my reference point here. It's 8.11 meters. Okay, so we're going to come.
Okay, so I have a question here. Does the company provide this equipment? Generally, they most consulting firms rent it out from equipment suppliers. We used to have equipment suppliers come and visit the classroom, but they get so busy it's hard for them to come. But yeah, if you attend a conference or anything like that, you can meet all the equipment suppliers, and they basically supply the companies, whether they sell it to them or rent it out to them. But yeah, you don't have to own your own.
Come all the way out. You can wipe off the tape. Try not to
That's
twist
a
the
little
tape
bit
too much as well.
extensive. I usually just spray down my tape as it comes up.
Just dry it off as they come up. It's kind of hard for me because I'm by myself today, but if you have someone to rinse it off with DI water, distilled water, that would be good. Otherwise, what you'll have to do is do a triple rinse back on the surface. So I just have a little DI water bottle. I'm just going to squirt it off. Ultimately, it'd be nice to do that with the whole tape. Again, what we always want to do is avoid cross-contamination. Okay, tighten the nut to the reel so it doesn't backspool on you. Turn it off to save batteries. Loggers. So I'm going to do it automatically with data loggers. This is a Schlumberger.
So we've already covered that in the last.
Then I'm going to run on the diver.
Fast forward a little bit.
Pull up the slug, and what's that's going to happen is as I remove that displacement, the water level is going to drop, and then it's going to rise again. So we're kind of getting a 2-for-1 test, and whether it's a falling head test or a rising head test, it'll be nice to compare the data. They should be about the same. So we're getting a 2-for-1 test and doing it both ways. Okay, so here is my slug. This is a pre-made slug from a manufacturer. You obviously have to make sure that the outer diameter of the slug will fit within the inner diameter of the well. We're dealing with a 2-inch well, so that's obviously important. So this type of slug doesn't have to be bought externally. You could just take some PVC, fill up with rocks or some cement, anything that causes a displacement. It'd be nice to ultimately know the volume that you're displacing. But again, it doesn't have to be a fancy slug. What is important too is that you tie it off really well, and you don't want to drop this and have it fall down the well. So it has some significant weight to it. So what I'm going to do is I'm going to basically introduce it into the well, and the data logger is capturing data right now. So let's see what happens. And that's why it's nice to have the data logger significantly below this slug so we don't get a collision. Okay, so I have buoyancy, and I am just going to tie off my slug here and let it stabilize. Okay, so I'll think about what's happening. Is I've introduced the slug, the water level is coming up, and now I have to give it time to come back down. So I'm kind of blind here. This type of data logger allows me to not get the data directly. To get the data, I'll actually have to pull it off and put it into a docking station to download the data. Some data loggers aren't like that. They actually have a cable attached where you can get a digital readout right away. That's not the type that I chose to purchase for a educational environment, because I would rather have more data loggers for all the students than to have fancier data loggers and to have everybody look over each other's shoulder. So what I want to do is, with that kind of safely tied off, is now I can bring my water level meter back, right, my Solensed, and now I'm going to monitor basically the fall of the water level. And I should be back to where I started, which was 2.72 meters to get equilibrium. Once I've established that, then I'll continue pulling out the slug and then watch for the rise in water level. Okay. So again, the depth of the same reference point. Okay, so right now the water level is at 2.56 meters. So it has raised with the displacement of the slug. And now we'll just kind of keep on monitoring it until we hit the static water level.
Okay, so now what's happening here? What's happening here is that they have so basically what was being described is you've got your well. That's the static water, right? He measured it. I don't remember if you guys noticed. He measured it, I think it was 2.75, let's say, meters below ground surface. Then he dropped the slug, and then it raised the water level. And that was 2.56, I think. And now what's going to happen is that over time, this level is going to stabilize. And what you can do is you enter that data, that how long it took. So in this case, let's say you've got the static water level minus, or the dynamic water level, the new water level, minus the static water level. And that's going to be large at the start, but it's going to go down over time. And how fast this stabilizes helps you determine K. Now, something I want to point out here, which is going to help you in your lab number 4. So I'm going to set up a scenario, and I want you guys to remember this. So you want to know how long it took for the water to recover 37% recovery or recharge of the well. So let's say you've got a situation here. Okay, we've got a well performing. In this case, we remove a slug. The static water level, let's say it's 2 meters below grade. We remove a slug of water, a little amount of water, or we pump out some water. And now the dynamic water level at the end of pumping is 3 meters. And then we watch the recovery. So we've got initially the difference between the two. So what that would be called drawdown. So drawdown would be, in this case, the dynamic water level, 3 meters minus 2 meters. So that's 1 meter. That's the drawdown. So at the start, the drawdown is 1. But as the water keeps filling up, the drawdown reduces. And what you're looking for is you want to see how much time passed for 37% recovery. Meaning, how much time passes for this to recover 0.37 meters. Does that make sense to you guys? This is going to be helpful to you in the lab number 4, where you're going to be using Horsley's equation. And that will help you determine K. Once you know K, based on this type of test, once you know K can help you determine, which is the hydraulic conductivity. It can help you determine the flow rate or the velocity. And that will be of high importance in a remediation project of a spill. So, coming to the next item, we can use software to enter this data and calculate this. So let's see. Act2Solve is one of the more famous ones. So let's see a demo for Act2Solve. And then we'll take our next break. And then we'll continue with the last part of today's class. So Act2Solve. We don't have time in the class to work on it. And it's a little bit pricey, so we haven't really done anything with it, but you can download the demo version. Let's go ahead.
Commercial software calls Aquifer to determine parameters such as transmissivity and storativity for Aquifer. So first thing is you need to download the data. Download the software. So Aquifer provides a demo version of that, which is free. But if you do actually look for the full functionality, then you have to pay for the price, which is around several $100s. Okay, so once you download your data, once you download your software, then let's take a look at the questions that we have. So basically, we are just having like 2 wells. One is a pumping well, and then which is penetrating a confined aquifer with a constant flow rate. And then we have an observation well that is 60 meters away from the pumping well, and then take measurements of the drawdown. And then the question is asking us to use the Thai solution and the Cooper-Jacob approximation to determine transmissivity and storativity. So here's the data. One thing that you want to make sure is that all of your units are consistent. For example, the Q is in a unit of cubic meter per day, but the measurements are like recorded in minutes and then meters. Okay, so now let's go to Aquifer. So now let's go to Aquifer, and it seems that there are some it seems that there are some technical issues with my recording, but probably should be fine. So the video clips are slightly like discontinued, but okay, never mind. So now let's just open Microsoft, and then basically you wanna so you click the thing here, and so which is new, and then you wanna determine that what exactly that we are trying to do. So we are basically simulating or determining the parameters using a pumping test. So which is a pumping test wizard. So they call everything as wizard, as you can see here, and then click OK. And then you want to determine, are we going to have multi-well tests, which is you have a jaw down measuring an observation well and the water is being pumped at a pumping well, versus a single well condition, which is jaw down is measured in the pumping well only. But here we are the first conditions, and then click OK, and then next. And then here's the place that you need to tell Microsoft what exactly units that you're working with. So we have a length in the unit of meters, and then we have a time unit in the unit of minutes. And then there are also like you can determine your pumping rate correspondingly, like so there are some of them like a gallons per day, etc. And then hydraulic conductivity, you can also change those values as well. And then you click next. And then you can always, so suppose you're an industrial professional, then you can specify your company name. Here I'm just listing as a CE173. Then there's another thing that we need to tell Microsoft. So what is the aquifer saturated thickness? So in the question it doesn't really specify, but let's just assume it has a saturated thickness of 8 meters. And also we assume an isotropic condition for the hydraulic conductivity. So which is
when it means isotropic conditions, you're telling the software that the aquifer parameters and properties are the same in each direction, horizontal and vertical.
KV divided by KH equals to 1, and then click next. So this is a place that we specify or we set up our pumping well. So the first well that comes up is usually the pumping well. So you can rename that into pumping well. And if you actually have a geological report, you know exactly where you install your pumping well, then you will have your well coordinates as well. But here I'm just leaving them as 0, 0. And then there's the well configuration. So for this question, we are working with a vertical full penetration condition. But if you do have problems understanding what exactly those means, like a partial penetration, what exactly does it mean, then you can always go to this help. And then click next. And then here's the place that we want to set up some specific numbers for the devices that we are using for pumping tests. So also like the question doesn't really specify those numbers, so I'm just going to put some numbers here. So assume an inner and outer radius of 0.3 meters. And then click next. So this is the place that you can specify your data set. So I copy paste the data from the PDF file. And then here is the place that you need to specify your pumping rate. So here, as we can see that the data that we have is basically a constant pumping rate. So it doesn't really matter too much. However, in certain kind of conditions, your pumping rate may be different, then you will just change correspondingly. And then after you do this pasting, you can see, I mean, the first row doesn't really have the data, which doesn't really matter too much. And then you click next. And then here's the place that you tell Microsoft where exactly your observation well locates. So it's from the question is 60 meters away. So we just put a 60 there and then click next and then next for this as well. And then we leave this the same as what we did before for the pump well. And then this is a place that you you tell Microsoft what is my jaw down measurement. So I convert the units as well, and then you copy and you paste. And then you click next. So this is all the things that we need. And you can see that the error log identifies error detecting your data set. Choose a view when you see the check errors indicator on the status bar. And as you can see, the fonts that are being highlighted as right shows that no errors detected in the data set, which means that we're all good to go to determine our data. So for example, we can displace the time and displacement. So this is also related. So we can see that the time is in a log scale, and then which is usually that how you can do that by hand as well. And then this is the data that is being showed up here. And the next thing is that we want to feed some solutions. So first, we can, it's basically you click this match and then solution, automatic solution doesn't matter too much. And then you have to activate the solutions. So solutions that's currently inactive. And then here we are working with the confine aquifer. So you click confine aquifer and you can choose a Thai solution or a different kind of solution. There are all different kind of solution that is being available. And if you're interested into knowing what exactly what solution represent what equations, you can always like check those things on the left, as you can see. So here I'm just going to use the first one, which is a Thai solution. I mean, and actually you can, and then because we don't really have a recovery data here as well, and then click OK. So now you can see there's a line showing up, which is basically the best fit.
So this is basically indicating which calculation method you're using. Right? The horse love is the one that you're going to use for your lab, but in the software you can ask software to use all these different types of methods. And when you're talking about confined aquifer, you're telling the software that it is not exposed to infiltration from the surface, that there's a confining layer above the aquifer.
So you can, and then because we don't really have a recovery data here as well, and then click OK. So now you can see there's a line showing up, which is basically the best fit based on the.
So anyways, that is what I wanted to share with you. Actisol. Again, you're not really going to be using it in this course. And so lab number 4 is where you're going to calculate the flow rate. And you've already started on the hydraulic gradient. So next week, what I'm thinking is I'll give you guys the second part of lab number 4, so you can do that on your own time. And in the theory portion next week, we'll use that to work on your projects to finish them off. Okay. All right. Now, I want to cover one more topic before we end the class today, but I'd like to take a break before then. So what we're going to do is we'll take a short break and then we'll start talking a little bit about superficial spills. Okay. All right. Okay, so let's get into the last session of today. Let's start off with a few things. So there's a couple of there's a few types of spills that we tend to deal with. So it might be an indoor or an interior spill in an office. So this could be in an office, sorry, in a factory, setting, or anywhere indoors. And usually what ends up happening is, so there's a few things. You should have a spill kit ready. Spill kit. Hopefully they have secondary containment. They don't always. And in certain organizations, in certain facilities, so let's say this is the factory, they will actually have drainage trenches lined up across the facility. So if a spill does happen in a drainage trench, and these trenches lead to an oil water separator. Now, spill kit could be kitty litter and so on. Now, the main thing that when you have a spill of a chemical is, number one, to protect people. So you must have hazmat suits and breathing apparatus ready, depending on the chemical. And you need to block drains. So you don't want to have the material going into drains like a sanitary or storm sewer. You do not want the spill to enter the sewer, because then you might have to get the ministry involved. Okay. Let's watch a corporate training clip about interior spill response and see what they have to say.
One of the founders of New Pig Corporation. We're serious about our role as the leader in leak and spill response. Your training needs led us to produce this and other videos relating to hazmat spill response. Extensive went into this video called Spill Drill. We hope it becomes an important part of your spill response training program. Let us know what you think. And now, Spill Drill.
So one of the things that I want to mention is, if you do see any of these type of organizations, they almost always have hazardous material MSDSs, or safety data sheets. Now they're no longer called MSDSs, now they're called SDSs. And those have the they list the things that you want to look out for. So it doesn't matter what kind of spill it is, but some of these steps that they're taking in the show, taking in this, we even take those steps outside as well in the exterior. You basically want to block off the area, block off the pathways, make sure it's not going to create an explosion hazard, and also make sure that the occupants of the area or the building are not under threat.
Look around. Liquids are everywhere. They have a definite volume, but no form. They're fluid. They flow. Some are harmless. Others are corrosive, reactive, flammable, or toxic. They are lubricants and fuels, paints and coatings, hardeners, degreasers, neutralizers, and acids. Wherever you have liquids, you have the possibility of spills, leaks, or releases. Most reportable spills occur in fixed facilities, factories, laboratories, plants, and mills. In 1 year alone, over 34,000 hazmat incidents were reported to the National Response Center. Over 60% of these spills involve small quantities, fewer than 10 gallons of hazardous liquid. Most people think that spills can't happen to them, but spills can happen at any moment in your facility. And that's why you must practice and be ready to respond. You must drill to be prepared for a spill. You need to know 7 simple steps. If you follow them, you will protect yourself, your fellow employees, and your environment. This is Spill Drill.
Just a date.
Hey.
Hi.
Very beautiful.
Sorry, I got a drink because I was nervous.
I had a couple in the car on the way over.
When a spill occurs, you have to be prepared. Start with familiarizing yourself with the facility's contingency or emergency response plan. You must be aware of the spill potential in your plant. Every minute is critical to keep everyone safe. Since no two incidents are alike, you have to be ready to take quick action. Response to a hazmat spill requires each of these essential steps. Assess the risk. Protect yourself. Stop the source. Confine the spill. Clean up. Decontaminate. And report.
Assessing the risk is a continuous work, not only just to address the level of protection and respiratory protection, but also throughout the cleanup, throughout the decontamination. This is a process that never stops.
The first step, assessing the risk, begins the moment a spill occurs. You must recognize the potential dangers and act immediately. Sometimes, no one is present when a leak occurs. The instant you discover it, you will begin to assess the risk the spill represents. When you notice the spill, ask yourself these questions. What substances are involved? How much liquid has spilled? How dangerous is it? Does it represent risks to life, property, or the environment? It is essential that the spilled substance be identified and any complicating factors recognized. You must recognize what you can and cannot safely do. As you work on spills, things will be changing. The dangers may lessen or they may increase. Risk assessment should be constant. This is very important. But before you take action, make sure you are protected.
The way that you protect yourself is by wearing chemical protective clothing. So if you're going into the hot zone to do some type of a cleanup, you need to wear the correct gloves, the compatible suits. You have to wear the correct respiratory protection. You have to justify air purifying respirators. You have to justify self-contained breathing apparatuses.
Select the right level of personal protective gear depending on the severity of the spill and the chemicals involved. No one kind of suit protects against all hazards. You may simply need goggles, a rubber apron, boots, and gloves. Or maybe you'll need a fully encapsulated chemical suit with flash protection. If you're uncertain, assume the worst and use the highest level of protective gear. Exposure by inhalation is one of the most common injuries suffered by hazmat teams. And one of the most common mistakes is using air purifying respirators instead of a self-contained breathing apparatus. Whatever you use, you have to make sure that it fits right and it's clean, decontaminated, and sanitized after every use. Always use the buddy system. Never handle a spill on your own. In dangerous situations, suit up in groups of 4. You will need radios or other reliable communications between team members. Don't think your safety gear makes you untouchable. Chemicals can penetrate through your suit, boots, or even your goggles. Suits can get punctures, tears, and seam rips. Over time, equipment can degrade from natural wear and tear and improper storage. If chemicals break through any of your protective equipment, leave the spill area immediately. Protect yourself. Choose the right size suit and be careful when you're working. Watch how you bend. Never kneel on rough cement. Avoid rubbing against something that could rupture your suit. Chemical mixtures can change everything. The way they react with each other can make a big difference. If you're unsure of their reaction with each other, assume the worst and dress accordingly. Your eyes are safely covered, but you can't see as well as usual. Your feet are protected, and your body completely shielded, but you can't move easily. And you're often very, very hot. The breathing apparatus makes this even harder. With all these handicaps, you're going to have to be highly responsible, more efficient, and more observant than ever. The time of an actual accident is not the time to fumble with unfamiliar gear or procedures. You must protect yourself and others. Keep people away from a hazmat spill site. The area immediately around the spill is an exclusion zone or hot zone, which no one should enter except protected responders. Surrounding the hot zone is a contamination reduction, or warm zone. An access corridor is established through this reduction zone. It should have an inbound and an outbound lane, and it is here that workers and equipment will be decontaminated. The support or cold zone is where the command post is located. If you're dealing with a spilled liquid that vaporizes, you will need to monitor the air. Vapors may be invisible and drift, so the exclusion zone will be much larger. Vapors may be heavier than air and sink and spread, or they may be lighter than air and rise and disperse, or rise and become trapped. You may encounter isolated pockets of vapor. Other questions to ask yourself are, how much liquid is spilled? Which way is it moving? And what's in its path? You must try to keep contaminants out of soil, groundwater, and water.
So essentially, many of the steps that are being mentioned are steps that you could also take, whether it's an outdoor spill. So this video, it covers off a lot of the basics. And I want you guys to pay close attention to this because this is one of your final project questions.
Waterways. These are a lot of steps. That's why you must keep practicing and familiarize yourself with the procedure and equipment. It is
not project, final assignment, final assessment.
Critical that you are prepared.
After assessing risk and dressing appropriately for the hazards, you've now contained the spill. But remember, say it's a 55-gallon drum, that spill is still leaking. So we've contained what's spilled, now we've not need to stop the spill. Well, how are you going to do that? Based on your container, whether it's a 55-gallon drum, whether it's a tank car, whether it's a 9,000-gallon tank truck, you're going to stop the leak to prevent that spill from getting larger. The sooner you can stop the leak, the smaller your incident remains and the easier it will be to mitigate.
Stopping the source may be a simple step, such as uprighting a container or rolling a drum so that the leaky side is facing up. You may have to turn a valve or an emergency shutoff. You may have to plug or patch a leak. A temporary repair job with a wooden dowel could do the trick. Self-tapping screws or a special quick-setting epoxy could stop the source of the spill. Contents of a spilled drum can be transferred to a new container. A reusable patch can be applied. Each situation is different. That's why you should familiarize yourself with the options to stop the source.
Confining the spill means that you want to reduce the amount of the fingerprint, the spill, as much as possible. And you do that by different ways, depending on the material. You can dike, you can divert, you can dam, you can neutralize, you can absorb. These are all different types of supplies that you need on hand for you to be able to perform this function.
Confinement means limiting the spill area. The faster you can stop the source, the less liquid you'll have to recover. Generally, the sooner you can confine the spill, the less area you'll have to decontaminate.
So these are called booms or absorbent socks. Different people have different words that you set up, and these absorb and they contain the spill.
Later, for a very small spill, you simply wipe it up. For a larger spill, confinement might mean diking, damming, diverting, or otherwise confining the liquid to keep it from spreading. The key to successful spill response is having the right equipment on hand and knowing how to use that equipment when a spill occurs.
So for that, you have something that's called a spill kit, which has all of these items ready to go.
Mats, socks, pillows, loose absorbents, booms, even non-absorbent dikes and drain covers can speed containment and response. Spill kits should be designed to suit your specific spill potentials, and spill supplies should be checked.
So these are all set up based on the chemicals that you're using at your facility. And this type of work, if you join a company and you become their environmental health and safety officer, So this is where you need to really focus on focus your expertise on spill responses and having the materials to respond to the spill on site. Like for example, if you have a spill and it's a certain chemical that that does not that cannot be absorbed with the spill kit that you have, then you've kind of wasted an opportunity, and you know, you could be putting your job, well, your coworkers are in danger, and the company's going to be liable for an extended spill, and you could also be putting your job at risk.
Replenished according to a regular schedule. To confine a spill, you generally start at the furthest point. A dam made of absorbent socks effectively stops liquid and at the same time makes the recovery process easier. Be sure to overlap absorbent socks in such a way that the overlap is to the outside of the flow. Otherwise, leakage could occur. It is important that your diking material be heavy enough. A strong liquid flow or large amount of liquid may require a secondary containment line. A non-absorbent dike is heavy, contains the flow, but does not absorb the liquid. As a rule of thumb, a dike's height should be twice the depth of the spill. A dike's base width should be 4 times the depth of the spill. A common mistake is trying to employ a dike too close to a moving spill. Give yourself a little distance. You don't want spilled liquid to reach the dike line before the dike can be finished. Confining the spill is critical to prevent the liquid from spreading to other parts of the facility and keep you and others safe. You must be prepared to confine the spill.
The Mitsubishi Outlander PHEV is more than one thing. Like you. It's electric and...
Once I've contained this genie, these hazards, inside of its container, this tells me if it's being released or did I do a 100% plug? Was I successful in plugging the spill? But we've got to make it safe. We've got to open up the area to public. We've got to open up the area back to the workforce. So the way we do that is by cleaning up. How do you clean up? Depending, do you neutralize acids and bases? Do you absorb solvents? Are they polar solvents? Are they non-polar? These are all addressed in the pre-plan. Then you have to take and you have to minimize is cleanup. That's another word for cleanup, minimizing. I need to take all of those contaminated absorbents, all those contaminated pieces of cleaning material and overpack them. Meaning I'm putting them in a garbage can. And it'll sit there in a garbage can that now we can move to a safe area. Maybe your facility has a garbage can or what is called a hazardous waste holding site for a private company or a third party to dispose of it according to the EPA regulations.
After a spill is confined, the cleanup stage begins. Some spills can be vacuumed or absorbed. Be careful not to step in the liquid. Always minimize contamination. There are recommended procedures and guidelines, but usually there isn't just one right way to get the job done. Take overpacking. There's the inverted technique, the roll method, and others. Whichever technique you use, remember, the goal is to prevent the spread of hazmat contamination.
Decontamination is simply put, is just cleaning up. Cleaning up people, cleaning up equipment. How do you do that? Based on your risk assessment, you'll know how to properly clean up.
Decontamination is the removal or neutralizing of hazmat materials that have accumulated on people and equipment. The first step to decontamination is prevention. No one should ever enter a dangerous hazmat spill zone until a decontamination area is ready. You may have to remove and dispose of clothing, or thoroughly scrub and rinse yourself with soap and water, or a chemical neutralizing solution. Decontamination techniques should be practiced so that you are best prepared when a hazmat spill occurs.
What proper reporting does, it not only lets people know what incidents have happened in this country, but it also prepares us for the next incident. We take the information from this spill We take the lessons learned and we build an SOP that tries to prevent this from happening again.
Hazmat dangers cannot be ignored. Be certain you follow all local, state, and federal reporting requirements, for there could be penalties for neglecting this. The law
Canada,
also requires
you
annual
report
training
it
for every hazmat spill responder.
to the Spills Action Center.
There are a few other factors you could have to consider. The spill site must be evacuated and safely cordoned off. Check on and off the site to see if someone was affected by the chemical, heat, or vapors. If you find someone, evacuate them through your decontamination and control zone. Look around for other complicated factors, such as open flames, heat or ignition sources, vapors, fumes, ventilation fans, wind direction, open drains, pressurized containers, strange noises, or anything else unusual. Be sure you spill drill. Schedule regular practice drills. Take each drill seriously because it may cost you or your friend a life. When a spill occurs, just remember the 7 steps that you practice in the spill drill. Assess the risk. Protect yourself. Stop the source. Confine the spill. Clean up. Decontaminate. And report. The more practice you have, the better those decisions will be. Hazmat responders have a...
Okay, so that covers that. Now there are guidances that I think I've posted for you guys. Let me just double check. Just double check. I've posted those. So these are pretty handy. These spill response kits, spill response, not kits, documents. Like for example, in British Columbia, what you need to do if you do have a spill. Right. Again, go through this, uh, and do the same for this document as well. Now, in this case, I want you to focus on. So this is the transportation of of goods. What I want you to focus on is the isolation and protection distances. If you have a spill, and I'm going to be giving you guys a project where, not a project, but a scenario where you might have to set up an area where there's an isolation zone, right? Because depending on the type of spill, so let's say it's a large spill at 208 liters or more, and if it's a hazardous material, you need to set up an isolation zone and make sure that there's nobody downwind that could be affected. All right, and that is based on the chemical that's going. Now, if it happens during the day, it's a little bit less of an issue because of the dispersion in the atmosphere. But if it happens in the night, it can have higher toxic levels or contaminant levels in the atmosphere. All right, so make sure that you take advantage of those items. Okay, and if you wanted to watch the video again or read the document about how to respond to the spill. Now, most companies will have a spill response protocol. Now, like for example, they will say, okay, one of the things you need to do is to call the Spills Action Center. Call the city that you're working in. Let your health and safety officer know of the situation. And essentially, the steps that should be followed are as listed here. They're basically it's the same or similar to what we went through. So check for physical hazards, right? Then if it's wet or muddy, be careful because you could have a slip, trip, and fall, and put up signage to warn other people. Next, evacuate the area if you're not able to handle it. But if you are, identify the source and cut it off. Let the supervisor know what's going on. Try to prevent the spill from entering catch basins or stormwater drainage areas. Use a permeable barrier or diking. You should have a spill kit for this. Now, if it does enter, then what you do is you try to block off this, or you try to divert the contaminant. And you need to make sure that you make the spill reported and come back for the cleanup as needed, as was discussed in that video. Okay, so that is the end of that. Any questions?
Professor, the documents that you were showing, is it shared?
Week 10? Do you see it in week 10?
Yeah.
So those will help you because there is a question in the final assignment, the take-home assignment. So either you can use some of the steps in the video, or you can use some of the steps we mentioned, but you have to outline a spill response. So it's going to be a question in your final. We do have, for the superficial spills, we do have one more session before the end of the course. Ruslan from the Spills Action Center will be coming and visiting us as a guest speaker. Okay. Do you see them? Should be visible.
Yeah. Yes, I see it.
It's in the lecture subfolder, all right? So what's going to happen next week? Just in case if it's clear, next week. This is what I'm thinking. It's going to be remote, but we will start lab 4 part 2. Okay, it's going to be remote, but it'll be lab 4 part 2. That'll give you enough time to finish off the lab 4. That's in the lab portion. And then it'll just be a work session. So if you want to attend again, online work session for the lecture, because you have a lot to finish off. So this will help you finish AOC assignment, which I was hoping you'd finish, but you haven't, and the term project. Okay, guys. But again, next week, both sessions will be online, but we will meet in person for your VS360 on Thursday. All right. With that, I'm gonna hand it over to you guys if you have any questions you want to ask.